Good morning, everybody. I know it's like 4 p.m. Good afternoon. So today we're going to be holding CPI's December contest review workshop, and today we're going to be joined by a team of amazing instructors from CPI who will be covering all the bronze and silver solutions from this month's contest, and we'll expect to finish around 5 to 5:30. So. If you guys have any questions for any of the problems, feel free to unmute or type in chat after the problem presentation. But um, other than that, we can just start off. So I'll hand it off to Rohan.
Hello everyone, so I'll be going over bronze round one. I'll share my screen. Okay, I'm sharing my screen. Let me know if you can see it. Okay, so basically I'll just like go over the problem quickly if you guys don't remember what the problem was about. And basically what's happening is there's n cows, n is less than 10 to the power of 5. And they have initial heights a of 0, a of 1, all the way till a of n minus 1, and the heights are all less than 10 to the power of 9. And then you have candy canes, that's also like around 10 to the power of 5, right, sorry, that have heights b0, b1, all the way till bn minus 1. And similarly, we have that the heights of the candy canes are at most 10 to the power of 5. So what's happening here is that for each candy cane, the cows like go through the candy cane in order. So you start with the 0th cow, and then you go up to the n minus 1th cow, and the cow eats the candy cane up to its height. So for example, I will pull up the sample case. And also the candy cane is not fall down. So if the candy cane was initially at like a height 7 and a cow of height 3 eats it, then the candy cane is now suspended in air between the 3 and the 7. So the sample case was something like, I don't remember the exact numbers, but it was something like 3, 2, 3, 2, 3 or something, and then 3, 6. Okay, so for this example, so we know that the first candy cane is height 6. So you have candy cane is from 0 x equals, or it's from 0 to 6. So first cow eats up to 3. So and then how much ever the cow eats, that's how much it gains height. So if you hear the first cow eats up to 3, so then the height of the first cow increases to 6, and the candy cane is from 3 to 6 now. Okay, and then the second cow, since it has a height of 2, it doesn't eat any part of the candy cane because the first cow's already eaten all of it, most of it, or up to its height, so then it eats nothing. And same with the third cow. And then for the second candy cane, we have the first cow just eats all of it. So we see that in the first and second candy cane, the first cow is the only cow to eat any part of the candy cane, and the final heights of the cows are 9, 2, and 3. So this is just an example, and this is gonna be helpful for us later when we're gonna try to like think of a faster solution to the problem than the initial one. Okay, so there's a pretty obvious solution that comes up, and it's basically for each candy cane you loop through the cows and you store the height at which the candy cane starts. So basically like you're considering like if you have like a line that's a candy cane and this is like 0, and then this is like the initial height, so let's say like h. Sorry, wait, my X is lagging for some reason. Okay, so this is like h. And basically every step we're considering like how high of a candy cane the previous cows have eaten. So like if let's just say this is like 6, so let's say this was like 6, and then the first cow eats the bottom 3, then we would store like height as 3 right here. So like make a new variable called like bottom or something. Bottom equals. So this is like the initial solution. And then basically for each cow, we can check if its height is bigger than the bottom, and it's and then we can add like the change in height of that cow is going to be its height minus bottom, unless the height is greater than h, which then you would just use like you can do like min of h and cow height minus bottom. And then if this is, and to make this even faster, you can just do like max 0 and then do this. So for any cow height, this is how much the cow will eat from the candy cane. So it's like a one-line way to do it. But then the only issue is since for each candy cane we're processing n cows, that's going the time complexity is going to be at O of mn, and this would time limit for some of the later test cases because you're doing around like 10 to the power of 10 operations, and that's way too slow for USACO to do. So there's some has to be some optimization we have to make. So this goes back to the previous sample that I was showing you guys, is that when you're going through like the cows, like usually what happens is that the first cow eats everything. So is there like a way we can rigorize it? And there is. That's just like how you would solve the problem. So I'll show you guys what we can do. So we can break up like any cow eating or any candy cane into two different cases. So I'm gonna call them type 1 and type 2. But like the name doesn't really matter. It's just like a way for me to reference them easier. So basically what's happening is that in a type 1 candy cane, the the first cow's height is smaller than the candy cane. So and then the second type of operation is when the first cow's height is greater than the candy cane. So we notice that a type 2 operation is O of 1, which means we only have to process one cow. And this is because if the first cow eats the entire candy cane, then we don't need to process any more cows. So for type 2 operation, we just need to check one cow and we're done. What about type 1 operations? So worst case for type 1, we might have to check all the cows, assuming that the candy cane doesn't run out by the time we reach like some number of cows. So the reason this like works kind of is because a type 1 operation can happen like there's no like I get it can't happen a lot of times. So the way we would rigorize this is that a cow every time a type 1 operation happens, the first cow's height gets doubled. So eventually the first cow's height is going to be greater than 10 to the power of 9 if there's a lot of type 1 operations. And once it's greater than 10 to the power of 9, since each candy cane height is less than 10 to the power of 9, then we know it must be type 2. So we know and this is written out here as well that uh okay, so like after at most like log 2 to 10 to the power of 9 operations, we can only have type 2. Because after this many type 1 operations, the first cow's height must be at least as much as any other candy cane. So this is like the basic idea behind the problem, and I can show you guys my implementation on the next slide. Does anyone have any like questions about the solution? Oh yeah, and then the time complexity for the solution is O of m plus n times log 1e9. But the log 1e9 is like a constant, so it doesn't really matter. So we can kind of call it O of n plus n, but it helps to like understand if you're trying to understand the solution, it might help to like put the log 1e9 there. So here's my implementation for the problem. And I did it in C++. So yeah, it's not that hard to change it in Python or Java. So basically, we first take the variables n and m. Oh yeah, and make sure for this problem to use long because it won't pass if we use integers. So basically you take in the variables n and m and you make two. Yeah, I can send a link in the chat. Okay, it's in the chat. So basically you take in the two integers n and m, and then you set up the arrays A and B, which have like the cow height and the heights of the candy canes. So then now you loop through each candy cane, and this variable cur stores how high we've already eaten. So it starts at 0 because none of the candy cane has been eaten yet. And then we use the formula I showed on the slide, is that the change is going to be the minimum of the cow's height and the candy cane height minus how much has already been eaten, and then make sure to take max in case the height of the cow is less than the current height. And then you just like change all the variables. So you set cur to you add change to cur, which means like um we've eaten change more of the candy cane. And then you also add this to the cow's height because it gains that much height. And then this is the most important part of the code, is that if the height that we've already eaten is equal to the candy cane height, in other words, we've eaten the entire candy cane, we break out. So if you don't have this like code right here, then you're gonna time limit. But this makes this fast enough. And then finally, you just output the heights of the cows. So that's pretty much it for the implementation. Anyone have any questions about that? Okay, if not, I'll pass it off to the next person for problem 2.
Right, contact tracing 2. So, um, it starts, the input is pretty simple. You're given the final cow state of an array of cows. All the cows are either sick or not sick. And we know that some cows started out sick and each day adjacent cows are infected. So for example, if it starts out as like 0, 1, 0, the next day it'll be 1, 1, 1 because the one in the middle infected both of the cows to the sides. Now, okay. Now, what we're trying to find is the minimum number of cows that could have been sick in the first place. So if, for example, the final, let's just like 0, 1, what's the sample case? Let me look that up again. See, in the sample case, the first one is just one cow can start out sick. Really, you can put the cow anywhere here and it could have resulted in this final state. And the next one, it's actually 4, due to this explanation here. But if you read the problem, you should know how this problem generally works. Now, the issues here, I'll go through this one by one. So in problems like these, it's helpful to establish like, why can't I just do this easy thing that just makes this answer the smallest possible, the largest possible? So like, what's preventing us from just placing one cow and calling it a day? And the issue here, is that the sickness can't skip cows. So if we have a final state that's like 101, then that means that 2 cows have to start out sick. Like this, we can't just place a cow here and hope that the sickness magically skips the middle cow and infects the one on the right, because that's not how the sickness works in the problem. And so that leads us to the natural follow-up question, which is, why can't we just place one cow for each consecutive sequence of cows? And the problem with this solution of sorts is that the sickness doesn't stop spreading once it reaches the final state. For example, say we had this sequence of states. Now, if we just placed one cow here and one cow here, then the cow here would need at least 2 days to infect all its surrounding cows. However, the cow here, it doesn't stop at 2 days. Like the sickness doesn't care whether it's reached the final state or not. If we just placed the cow here after 2 days, it would have been like we would have had 5 ones instead of just 1 surrounded by a couple of zeros. So does everyone understand how these constraints work? Like, does everyone understand the answers to these 2 questions? All right, great. So let's move on to, yeah, basically you just have to make these two assumptions and that essentially solves the whole problem. So we first look at all the sick runs of cows individually to get the maximum number of days that could have passed without the runs overflowing. So for example, let me bring up this example here again. So here, this this cow this run could have had you could have left this run for a maximum of 2 days without it expanding out of the bounds given to it by the final state. Here, on the other hand, it can only have only one, like I don't think any days can pass. Just you just place the cow that's initially sick here, and that's it. There is one edge case that you have to handle. It's when the run ends, like it's at the border. Because in this case, you can have, if you have a run of 4 at the end, you can have 3 days instead of just the normal one, I think, without it going out of bounds. That's because you can place a cow here, and it can't expand past the edge because that wouldn't make sense. So it just expands here 3 times. And yeah, that's the one edge case that we have to take into account. And after we get the maximum number of days that could have passed, so we can place the minimum number of cows necessary. We then go through all the runs again to get the minimum number of initial sick cows. And here, let's go to the implementation. I'll share the link here. All 3 languages, I think I could. Yep, all 3 languages are here. But since the Python one is the shortest, and it should be pretty intuitive what the Python code is doing, I'll just go over that one. So here we just read input, pretty standard stuff. And Python actually has a split function, which works really well. Instead of like iterating through the runs, I think the Java solution iterates over the runs. Or is that C++? No, yeah, that's what C++ does. But in Python, you can just split it by all the zeros, and it'll return all the consecutive runs of anything that isn't 0. So, and here we calculate the maximum number of days. So first of all, if the length of the run is 0, we obviously don't do anything because like that's irrelevant to what we're trying to calculate right now. Here, we check for the edge case that I mentioned earlier. If it's the border, we get the maximum number of days that could have happened is the length of the run minus 1. However, if it isn't at the border, we have to divide it by 2 because say like if it was at the middle, the maximum number of days and for this run is 2. It can't be 4 because like it can go past either the left or right end. And I believe the final thing in the Python solution is just to iterate over the runs again. Someone asked what the assert function does. It's just a very rudimentary form of input validation. You could remove this from the program and it would still run just fine. Let's see here. Here we calculate the minimum number of sick runs. And then we take the length of the run and divide it by 2 times the maximum number of days. If you're confused by this formula, just run this like for some sample input yourself. And then you'll see why that's the case. A small oversight here, this I variable isn't used, so I hope you guys don't get confused by that. Can all the edge cases be 1? So if it's a 1 on the edge, it takes, yes. If it's 1 on the edge, it should still take, the maximum number of nights should still be 0. And someone asked, can all the edge cases be 1? Could you elaborate on that a little? All right. Okay, so let's see here. Let me try and perhaps if I can you guys see my terminal right now? All right, so let's see here. 1110000 dots. Let's call this split function, which should return all the consecutive runs. Now, as you can see, there's a bunch of empty strings. Again, these are handled by the length check. These don't matter. A very quick tangent. If you're confused by the Python, you can just look at the C++. It does essentially the same thing. If there's one cow sick at the beginning, it would still work. I'm not sure. Is your test case, is there one at the beginning or no? Um, let's see here. If we split this at 0, then you'll see that it handles the borders correctly. Like there's a 1 at the beginning and a run of 1s at the end. And these are handled by the index check. If the index is 0, or if it's, in this test case, if there was one cow. Yes, I believe. Yes. The answer to okay, so again, I'm not 100% sure, but if I understand your question correctly, the answer to this test case here, it should be 1. It isn't 2, but if you're, does that answer your question? All right. I'm gonna assume that's a yes. If you still have a question, then feel free to ask in the chat. But for now, I am going to pass it over to the next presenter.
For this problem, I guess to just reiterate, so you have a row of plants that after you're trying to grow for a certain number of days, and each plant has a specific height. Plant one, let's say plant one has H1, H2, and plant two have H2, and plant three have H3. And so, and after each day, the plant grows by whatever. So the I plant grows by AI. So on day 100, the final height of the plant is H1 plus 100 times A1. And so we can generalize this. So on the nth day, you have H1 plus n times A1 for the first plant, H2 plus n times A2 for the second plant, and so on. So what the problem does is it gives you a specific order that the plants have to be ordered from tallest to shortest, and you have to find the minimum number of days for the plants to be able to grow to satisfy a freeze condition. So the first thing I guess we'll talk about is what if there's only two plants, right? That's one of the subtasks which will grant you one test case, which is like 20 points, which is really good. So without loss of generality, let's say the first plant will label H0 and the second plant will label H1. And for the order, which is Ti, the first plant must be taller than the second plant. So T0 equals 0 and T1 equals 1. If this is not literally true, then we just swap them, right? So what is how much days do we need to grow these plants to satisfy so we can guarantee the first plant is taller than the second plant? Well, if H0 is already greater than H1, which means the taller plant is already taller, then we need to spend 0 days, right? Because it's already taller. And what if and then we'll consider if H0 is currently less than or equal to H1, which means it's not currently taller. So here we also have two cases regarding A. So if the taller plant is growing it's going at a strictly faster rate than a shorter plant. Then what this means is plant 0 grows a sub 0 minus a sub 1 more feet, right? because that's the difference in the high growing rate. So what we can get from this is the number of days for the shorter plan to surpass the taller plan. It's just the height difference between the taller plan and the shorter plan. Plus one because we want the taller plan to be at least 1 feet taller, right? Or even 1 inch, I don't know. Over the difference in growing rate, right? And this will be CL. So this will round up. So we can guarantee that it's an integer. Okay, but so what if it's growing at a shorter rate? So the plant we want taller is both shorter and growing at a shorter rate. Then this is impossible, right? Whatever how many days we go by, then there's no way plan 0 will surpass plan 1 in height. So this will just return -1, right? So this is essentially the crux of the problem is, so now we have figured out how to grow plants for two plants, how to generalize it to a lot of plants. So what I'll do is I'll refer to the above algorithm as the checking algorithm, because this determines the minimum number of days for one plant to surpass another plant. So we can talk about the other subtask. The other subtask is n is less than 5,000, I think. So here you can do n squared algorithm, right? So imagine you have yes, a list of plants. S0, 1, 2, 3, A0, A1, A2, A3. And let's just say it's in order for now. We'll handle if it's not in order later, or I mean for TI. So the easy n squared solution is we compare each plan and we see how many days it takes to satisfy the invariant, right? So what we can do is we can run the checking algorithm on H1, H0 and H1, and then this will output this output an X, which is the number of days for the variant for H0 and H1 to hold true. And we can do the same thing for all pairs of plants, right? H2, and this will be Y. And then what we want is X, Y, dot, dot, dot. And this will go on for each pair of plants. So we'll check this, check like that, and then something like that. So this is n squared, which is not okay because it's way too slow. And so if you have this, you just want to take the maximum number of days needed, right? Because a checking algorithm already gives the minimum number of days for the invariant to be satisfied. So the observation here is to optimize to O of n. N squared is bad. You want O of n. So I propose that we only need to check plants that have consecutive TI. So I propose that we only need to check H0 and H1, check H1 and H2, then check H2 and H3, and take the maximum. And we don't need to check any other pairs. So why? So since we know the plant with a certain TI must be taller than another plant with TI plus 1. So if you call this TI and TI plus 1. So if we know that this plant satisfies, so we know that this plant satisfies this plant, which this plant we know is taller than this plant. And by the transitive property, then we also know it's taller than these three plants, right? Because since the first plant has to be taller than the second largest plant, then it must also carry over to the rest of the plants. And if we run the same algorithm on the second largest plant, we know the second largest plant is taller than the third largest plant. Then we know that, then we're basically creating a chain. And so it's equivalent to the n squared algorithm. So Now what? What if TI is not sorted? Well, if TI is like 3201, then we can initialize another PI where it stores a number J such that TJ equals I. So now we're able to get the index in TI such that we're able to get consecutive TI, and we're able to store the index in PI. So what this does is instead of using TI, using TI, we can just use T of P of I, since this is the actual index for the consecutive numbers. So lastly, I guess I'll talk about how they actually solve this problem. So what we can do is we can run a for loop from the plant with the highest TI, which means the plant with that's supposed to be the shortest, to the plant with the lowest TI, right? And since we established that we only check consecutive, so suppose at some point, let's say plants 0, 1, 2, 3. So it's here I'm assuming that TI is also sorted. So if we know that it takes d days at this point between, let's say between the first and between plants 1 and 2, then we know that all the plants before must also grow at least d, right? So here after d days, the new heights for the new plants will be h0 plus d times a of 0, and h1 times d times a of 1, right? So we know the minimum height that the plants that are taller have to be able to grow. So what we can do, we can just keep a counter d, and we can run the checking algorithm for each consecutive plant, and then we update the height of each plant to whatever d is at that moment, and then we're able to get the plants for new height. So the answer is just the d at the end of the iteration, right? And of course, if at any point you encounter -1, then it's no good. Then you could just return and print -1. So beware that this reveals another case you have to consider. So let's say we have a plant X and a plant Y, HX and HY, where we had T X I equals X. Okay, I'll change this to HI and HI plus 1. And we'll let TI equals I and I plus 1. So this means that the first plant might be taller than the second plant. But if we, at the end of the iteration, we might have such case such that HI time plus AI times D. So will our capital D be the number of days for all the plants to be able to finish growing? So if it's equal, um if it's not satisfied the invariant, so A plus 1 plus B. So note that this plant must be taller than this plant, but at the end it's not true. So you might be like, why could this be, right? Well, during the iteration, we might find that H1 times AI times D is little d, which means the number of days at the iteration is greater than, it's already greater than whatever plan that's supposed to come shorter. So if you run checky algorithm on this will return 0, right? But since capital D is greater than smaller d, then this might happen, right? This case might happen, which means the number of days at the end of the iteration. So when does this happen? So this only happens if we have HI is, or if we have A of I is already smaller than A of I plus 1, right? It's initially taller, but since it's growing at a slower rate, it might become shorter than the shorter plant at the end. So we can counter this just by doing like a final check just for the the simulation statement problem just to ensure that Farmer John's happy, right? All right, that's basically the algorithm. Are there any like questions? Maybe. And oh yeah, and if this case is true, then we output -1 since we know that if we grow more days than then there's no way for a plant that's growing slower to be taller than a plant that's growing higher. That's growing faster. All right, I guess we'll move on to silver. Yay.
All right, let's start with silver. Bovine acrobatics. Sorry about that. We have n less than or equal to 200,000 distinct weights, and there are A of I cows with weight W of I. So we want to create balanced towers. So this is essentially a bunch of sorted sequences of cows, such that the difference in weight between adjacent cows is at least k. So essentially, if we were to, I don't think we need to necessarily implement like a sorting thing here, but we just have a bunch of cows in, let's say, a set, an unordered set. The ones between the adjacent entries must be, the difference between the adjacent entries must be at least k. And if we want at most m balanced towers, at most how many cows can be in the towers? Here we assume that one cow can only be in one tower. A cow can be at most one tower. A cow can be in at most one tower. So I should probably bring. Okay, so a cow can be in at most one tower. So essentially what we do, the way we should think about this problem, right, is essentially as putting a bunch of like initial bases, let's say m such bases. And then on each base, we start putting cows down on each base from the heaviest up. So let's say we have like, I think the next slide has a bunch of examples. Yeah, so in this case, we would want to essentially, we have, I think, four bases because we can make at most 4 towers. First, so we have here 3 cows of weight 9. And then we have 5, sorry, wait, no, it was 5. We had 5 bases. We can do at most 5 towers. We have 4 cows of weight 9. We have 6 cows of weight 7. And then we have 5 cows of weight 5. So we should think of this as essentially dropping cows down from the heaviest to the lightest, because let's say that we dropped essentially a cow of weight 7, where we could have dropped a cow of weight 9. Then we see that if we could have dropped a cow of a heavier weight, let's say 9, then, okay, in this case, there's no conflict, so it doesn't make sense. But essentially, just assume that instead of having cows of weight 5, we had cows of weight like 6. And then we had like k equals to 2. In this case, assuming we dropped like a 7 instead of a 9 initially, then we can't really put anything on top of this. So in this case, it would be better to just instead put up a 9, because we would essentially be closing off potential options for putting more cows in if we just put if we put a lighter cow than we need to. So at each step, we should just come up with a greedy algorithm, which is put the heaviest cow down first. And then we can essentially simulate this process then. So we drop our 3 nines or 4 nines. And then after this, we would have 4 towers with base 9 and 1 tower which is empty. Then we would want to place 5 of the 6 sevens. Oh, assume this is a 5 again. But essentially we can put down 7s in all of our rows because k equals to 2, so literally every single row is then open. And then we have all the 5s. So we see here we used up all the 9s. We used all but one of the 7s because we can't stack 2 cows of the same weight, as that would lead to a violation of our balanced property. And then we put down all cows of weight 5. So here our answer would be 14. So because we used 14 cows. So this example provides sheds some light on the actual solution. So again, recall that we should always place the heaviest cows first because that opens up options for placing cows down afterwards. So the way we would do this is essentially sorting our weights from the largest to the smallest. And for each tower, we essentially want to keep track of the weight of the topmost cow, because if we place the cows down in the correct order, then we shouldn't create any violations that can't be checked for with the topmost cow. So to rephrase, if we place all of our cows down correctly to begin with, we only need to check the topmost cow in order to figure out whether or not we can place any more cows on top of it. So, but also because we have a larger sample, like a larger input size, we have to keep track of multiple towers at once. Because if we were to just individually drop every cow onto every tower, we would have like O of C time, where C is the number of cows, which is too slow. So instead, we want to do something that assigns cows to towers in less time. So essentially what we would do is keep track for each tower entry of the weight of the topmost cow and then the number of towers with that weight. So in this case, we would essentially have how heavy because all that really matters is how heavy the top cow is. So if we have multiple towers with that same top cow weight, those towers are essentially interchangeable when we want to put more cows on top, right? So when we place cows down, we essentially check all of our existing topmost weights and check for balance, and then we should do this in order from heaviest to lightest. Some implementation tips for this problem. If we want to insert the smallest values on the right and check the largest values on the left, we should use a queue. So my implementation is, I just have it on Pastebin here. So we first keep track of 3 numbers n, m, and k, as well as the existing weight frequency pairs. This is just input handling. So I just take in the input. Then I sort the cow weights in decreasing order of weight. So we would have this. And then I essentially create a queue that stores the current tower status. So this keeps track of the pairs with the topmost cow weight and then the number of towers with that weight, all in terms of the all in this queue. So initially we have a bunch of empty towers, right? So that's essentially like we have a cow with infinite weight, and we can literally place anything on top of it without breaking the balance rule. So I just have int max here. So this is going to be the initial state of the towers. And the reason why I just put these infinite weight cows down first is because I want to lock the number of towers at most m. So yeah. And then let's say we have like our answer here. So the reason why we can use a queue here is because when we place cows down, we're essentially let's say we have like an initial structure of like big weight and then like some number. So if I wanted to essentially put a bunch of cows with like a smaller weight and then a different number, I would first get rid of some cows in this block. So this would be like weight n minus m or something. And set this as the new front entry, since in C++ you can like modify like your entries in the queue. And then at the end, I then push in the new smaller weight and different number of cows. So essentially, it's an invariant that the entry on your left is going to be the largest entry, the highest weight entry in your queue. So that is essentially why the queue works. So here we essentially iterate over all of our possible cows that we want to put down. So we first have an integer saying the number remaining, and this would be essentially the number of cows remaining. And then after this, we have while we still have towers left and cows remaining. This is essentially checking: do we have towers? Do we have cows? And is the balance condition satisfied? And then if all these three things are true, then we essentially place down as many cows as we can on towers where the topmost weight is weights dot towers dot front dot first, I think. And there are two cases. First is where, let's just call this X. The first case is where we have more towers of weight X, which means that we essentially just put down all the cows that we need to and then move on. And let me just call this Y. The second case is where we have more cows of weight Y, in which case we just take everything, essentially take all of the place cows on all available towers, remove that pair of like topmost weight and number of towers, so we don't place more things, and it just like unclutters the queue, I guess, so we can reach the next item. And then we just iterate again through this while loop. And this is why, again, it's a while loop and not an if statement. And at the end, let me clear all this so I can scroll down. At the end, we essentially have we essentially want to put down all of the cows we need to, which is going to be this value over here. And then the rest of the cows we have no place for because we've already looked through all the tower tops and we have not found anything that we can use. So because either we're out of towers or all the subsequent towers don't satisfy the balance property. So yeah, at this point we're essentially done, and there's we've placed all the cows we can place, and everything else is unfortunately we unfortunately can't place it. So yeah, we just push a new topmost weight and number pair, and that's going to be the tower that we place at the really end. So yeah, that's essentially the logic for this problem. So I'm just going to open the floor up to see if anyone else has any questions. Okay, if there are no questions, then I think that we're good to go for the next problem. Wait, hold on. Okay. So yeah, I think that the implementation is here. Anyways, I think that the implementation here is going to be on the paste bin if you need it. So second problem is we have n barns of which there are k distinct pairs, and we have essentially two numbering schemes for the barns. I think in the original problem they said something about like Annabelle and Bessie counting the barns differently. But essentially what we have is that Annabelle says that barns A sub 1 through A sub k are in that order in a cycle. And Bessie says that the barns B sub 1 through B sub k are in that order in a cycle. So I think in one of our examples, we have like Annabelle says that we have barns like 1, 2, 3. And then Bessie says that we have barns 4, 5, and 6. Wait, why did it go back to 4, 5, and 6? Oh, that's why. And essentially, what Annabelle thinks barns 1, 2, and 3 are what Bessie thinks barns 4, 5, and 6 are. So in this case, we want to find the largest number of barns that can be numbered the same in both numbering schemes. So our first step is to notice that if a barn doesn't appear in either cycle, then it can be the same in both numbering schemes. Because we don't actually know what each of those barns are numbered, and we don't have any constraints on them. So we can just assume the best and just say that they are always the same. Otherwise, a number can only overlap if it appears in both cycles. And even then, only if their positions line up. So we just check which rotations of the second cycle will match each entry present in both cycles. And then we can just choose the one with the most common entries. So essentially, the dumber way to do this is essentially to rotate our rotate the array B multiple times and essentially just run like a left to right check just to see, okay, which ones match on each rotation. A smarter way to do this, I think, is to create like a map of all of the offsets. So let's say, how much would we need to rotate this array in order to have the position at A be the same as the position at B? And whatever number of like cyclic shifts we would need, we can keep in like an offset array, and we just find like the most commonly appearing value in that offset array. So yeah, here we just choose the one with the most common entries. And then, yeah, also the problem technically says that you can rotate you can like reflect the cycles. So you also should just like reverse the array and run the same check again, for example. My implementation is over here. We essentially have a bunch of like imports, and then just input handling over here. And then, yeah. So first I wanted to check for which barns were just not in the cycles at all. So I used set and just did this, and the initial value would essentially just be n minus the number of entries that I found in the set. I can do this because, yeah, set doesn't have like duplicate values. Secondly, then I went and count the cycle. I used a for loop because I wanted to do both like the forward version and the reverse version, and the logic should be the same for both of them. So we have first a vector that finds all the indices in cycle A, and then a vector that finds all the indices in cycle B. Afterwards, we would have to take a map and essentially find all of our offsets. And yeah, so our offsets are first just going to be like the number of cyclic shifts in one direction, because if we try to keep track of like positive and negative shifts, then that's going to be kind of annoying. So I essentially just normalized it to 0 through k mod k, and then normalized the offset from 0 through k mod k, and then took that normalized offset and put it into the frequency map. And here, after normalization, our offset can only be between the values 0 and k. So I just took those values and found the one with the most number of occurrences. And we can repeat this for reflections of the B array in order to get all possibilities for our answer. And then our answer is just going to be initial plus cycle. So yeah, this question was a bit more straightforward. And yeah.
I'll be covering the problem target practice from the 2023 December silver contest. Okay, so Bessie's a robot and she's on a number line trying to shoot T targets. She's at position 0 and apply this string of C commands, which either moves her one to the left, one to the right, or she fires and if the target at her current position is hit and destroyed and cannot be hit again. And if we're allowed to change up to one command in the string to a different command before she starts like following it, what's the maximum number of targets that Bessie can hit? Okay, cool. So, for example, in here, we have the instructions left, fire, right, right. And our targets at 0, -1, and 1. So, without any changes, we go left 1, which takes us to -1. We fire there, which hits a target. We fire again, but it doesn't change the number of targets that we hit. since it's gone already. And then we move right, fire, so we get the 1 and 0, and we move right again. And the most optimal change we can make is, or one of the ways that we can change it, is if we change the last one to an F, we can shoot the one at position 1 as well, which gives us the total answer of 3. And for here, we just keep firing at position 0, so we can just leave it unchanged, and we get 1. And for this one, our answer is also 3. Okay, so let's talk a little bit about like observations and like what we can gain from this problem. First of all, the bounds t is less than or equal to 100,000, and so is the string of commands. So we probably can't do any like call it. I can't do like n squared robot if you remember the USACO guide, high complexity module. So we can't just change every command and see how it affects it, right? That'd be too slow. So is there any way to like summarize how a command change or affected targets? Best defies that. And really like changing command just shifts everything by a certain amount. So let's talk a little bit more about how you can like deduce this observation. So initially, like the most naive way of like solving this problem is, oh, maybe we just switch like all the commands to everything that it couldn't be, and we just would do everything. Because like the time complexity of um getting the answer for a fixed like set of directions is, let's say, finding answer for a fixed set. We can do this in open time because we can just iterate through everything and just like simulate a position like we did here. And so now we can think about how many changes we have to do. Well, for all the instructions, we can change it to like everything that's not. And since you have 3 instructions, we have 2 times C number of changes. Actually, it should be C. C possible changes. And so our total time complexity is just going to be O of C times 2C, which is just O of C squared. And this is actually okay for the first subtask, because we're given that T and C can be less than or equal to 1000 for this first subtask. So this is actually okay for TC less than 2000 or less than 1000. And this gets us like 3 test cases, so probably not the best we can do. Okay, cool. So now we can just kind of like play around with changing certain instructions. So we like the biggest time waster here is that we have to like recompute every single like we have to recompute the answer every time we like make a change, and that takes OFC time, which adds like a pretty big factor. So we could think like, oh, is there a way that we can like reduce this problem so that we don't have to like reiterate over everything? So okay, so if we just if our like commands, if they were right, left, right, right, left, and if our position, this is going to be 1, 0, 1, 2, 1. And so we just changed the second one to like, wait, let me just put some space here. If I do that. Okay, never mind. What's that? Okay, cool. So if we can imagine just like changing the second one to an I, what this becomes is just I, 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 which is 1, 2, 3, 4, 3. So clearly everything like in this section before the change remains the same. Or yeah, everything in this section remains the same, right? But everything after that kind of has like something great going on. We can observe that for every position here and every position here, there's just like everything on the left is what it is on the right minus 2. Like 3 minus 1 is 2, 4 minus 2 is 2, 3 minus 2 is 1, so on. So we can kind of make this observation that whenever we change a command, what we do is we just shift everything like on the right by some amount. And this is actually really important because we know that we can only make at most one change. So like there are only so many like we don't have to like layer these changes on top of each other. And so we can just kind of do like the casework for like possible changes. So if what it was like before, let's just say before and after, say like change. So if it is an R before and now it's an L, what we have is we're gonna go right, but instead we go left. So we're gonna be like if it's at 0 and it's like just right left, we're going to be at 1, but we end up at -1. So this is a -2 change. And same like wait other way around, this is just +2. We have our other operation, which is a fire, which is gonna be kind of a tricky case in implementation. But f doesn't like it doesn't change our position at all. So this is gonna be a -1. This is gonna be +1, and then everything else is just 0. Okay, cool. So now we confirmed that like at most the suffix of our like position of our positions is gonna be like shifted by at most +2 and at least -2. Yeah, so this really reduces the amount that we have to check. So if we like think of having an array like prefixes and suffixes, okay, I would say this, say, then this is just gonna be like the targets that we hit. We have like suffix of I, J, say, um, targets hit from I to C and with J offset. And this is because like whenever we do a change, it affects the rest of our positions, right? So we can like imagine a split in our yeah, we can imagine a split um in our like arrays, right? Because everything above this area is gonna stay the same. And everything below is gonna get shifted. Okay, just say no. Okay. Cool. So then if we like change a specific um character, we can just say, oh, like a potential is you can say like answer, um, or just say like what is called as a transition. You can say this is if we're at like a position I, at position I, and we change it from and we change it, then we can just say our maximum answer is equal to the maximum of our answer, the prefix at I, or really this is at I minus 1, right? Plus suffix of I to our offset, and maybe possibly like if a target exists at I, say target exists at our current position, and we only consider this if we're changing it to an F. So this only if changing to F. And then for the rest, we can just look it up in our like offset table here. Okay. So that's basically the problem. And yeah, there is kind of an implementation quirk where if we take something in a prefix, we can't take it in a suffix because we're not guaranteed that like we always go like forward and back, right? We might go like on a number line. What terrible line? Let's do good. We have a number line, then best you could go like this and then like turn around. So we need to be careful that like once Bessie takes a target in a prefix, it's not taken in a suffix. And to do this, we can just update our suffix array after we process. So if like during a prefix we just like gain, or like we hit a target in a prefix, say to avoid overlap. If we hit something in a prefix, or if we hit a target in prefix, remove it from the suffix. Okay, and then also something to note, this is gonna be like kind of a sticky situation if you store this as like a standard 2D array, right? Because actually, no, this is fine, it's fine. But yeah, we just need to make sure that like every time, like after we process a command, we just make sure that everything in like the suffix gets like updated. And this is it's just gonna be um like O of 4 to update this, right? Because you just need to update all offsets. Okay, cool. So let's talk about code now. Let's just make sure to cover everything here. Yeah, so you can just like consider all offsets. And apparently there was weak test data in the competition, so some code got accepted when it shouldn't have. But here's the link to the code. I'll be going through it very shortly. But Kevin kindly put in all of the languages. So if you're not like a C++ or Java main, you can go check out like Python, and everything is just like at that time. You just go for it. But we'll just go through the C++ stuff. Okay, so first of all, we're just gonna read in our I can include all libraries and stuff, right? And then we'll like read an input. Let's see. Okay, so we have our number of targets, number of commands, and we just read in targets. And commands too. Okay. And now we want to compute our our suffix array. So we can say we have the hits, which is a map of a map, which just stores like the targets that we hit if Bessie was offset by an amount. And so the second layer here is only gonna have, or the first layer is only gonna have 4 possible values, like D hits of like 0, D hits of 1, D hits 2, D hits -1, hits -2. These are the only things that are gonna be like used here, because this is gonna store our offset, and the second one's just gonna store position. So we go to here, we simulate our position, and then if it's a fire, then we can say, oh, did we hit anything? And could we have hit something if we were offset by some amount earlier? So we could just say, we either do all the positions that we could have been at, and then if it's part of our targets, then we can just increment the answer by 1. Okay, cool. And now we can go to a main loop. We're gonna once again keep a running position. It's gonna be like this, and then we will go do all possibilities. Cool. So in previous is just gonna say if we've hit like this position. Okay. So here is some casework. If C is LOR, then we can only change it to opposite sign, so we treat this a little bit differently. And if we have hit, this just says, oh, if we didn't move at all and we decided to fire at this spot, then would we like hit something? And it's just targets.count position, and that we haven't hit this position already, and that like and we haven't hit it in our suffix, then we can just say we can alter the answer to between everything that we hit already, everything that we will hit in the future, plus whether we hit right now or not. Or we can just change this to the opposite sign, which should be left to right or right to left. And this is going to be what we hit already plus everything that we'll hit in the future. And this is kind of like a bit of information quick, but sometimes too it just says, oh, like if we're going right, then like now we can just go left, and this will just be like -2 when we multiply it out. So that just gets us like um the offset that we need. Okay, and then now if C is F, then we can say, oh, did we hit anything at this moment? And so once again, we just say, if we did +1 here, instead, we can say d hits of 1 dot count position +1, and d hits of 1 position +1 equals 1. And this just says, is this the only time that we ever fire here? And like, do we reach this in the future? And the same thing for the left side, we just say -1. And so we can now update again. We say what we hit already plus what we'll hit in the future minus whether like now was the only chance we could have had at firing at this position. Okay, cool. And so now we need to update our suffix array to make sure that we don't double count. Go. Okay, so once again we're just doing like the same simulation work. If it's left, position minus minus, if it's right, position plus plus. If we fire here, then we want to make sure that we don't hit it at all in the future. So remember targets is like our like set of targets. Now we can just like kind of what is that? Now we can just make sure that like it's removed from all of our like potential targets in the future. So we hit it, so we add it to a hit array, and then for everything in like our future suffixes that include this H, we can just erase it. And then again, we can apply a very similar algorithm to what we did earlier. We iterate over all the possible positions, and if like sorry, if we do hit it, they're making this subtracted from a delta, and then if it's less than or equal to 0, meaning that like it just like doesn't exist anymore, we just erase it as well. Okay, and then at the end, it's just gonna be the maximum between a max hit and then a like hit already. And this case is here because this is saying if we never make any changes, how many targets do we hit? So yeah, that's basically the code. Across C++ and Java and Python, the code is all pretty similar. It's just like syntax. So feel free to go check it out. And yeah, thank you to Kevin for writing the slides, and we'll see you next time.